Hello, this is a walkthrough of counting. Question 1 is saying the local library got itself a Twitter account. It appears to have been active for only a short time, but while it was running, it diligently tweeted one 140-character message per day. Assume that it uses only the 26 letters of the English alphabet plus the period, comma, and space, and that any 140-character combination is possible. How many possible tweets are there? Well, because there are 26 letters of the English alphabet, plus we're using 3 extra characters, we have a total of 29 characters available. So each character in our 140-character message has 20 different possibilities. So there's 29 different possibilities for the first character, 29 possibilities for the second character, and so forth. So thus we have 29 to 140 power different messages or tweets. Part B is saying how many tweets use no spaces. Well, because we want to use no spaces, we just remove the possibility of space being a possibility. So now we only have 28 characters that we can use. That means the first character only has 28 different possibilities. Second character can be 28 different characters, and so forth. So we only have 28 to 140 power different tweets. Part C is saying how many tweets consist entirely of white space. So if we want entirely of white space, there's only one possibility per character in our message. So for the first character in our message, there's only one possibility, which in this case will be the white space, because we don't want to use any other different types of characters. Thus, since each character in our message has to be a white space, thus we are left with 1 to 140th power, or just one tweet. Part D is saying, let T be some particular tweet. How many tweets differ from T by exactly one character? Well, if we want to differ by exactly one character, that means for the first character in our message, that it used one character, so thus we're left with 28 different other characters left we can use to replace it. So thus there are 28 different ways to replace the first character to make it different by one character. So we can do the same argument for the second character, which that means there's only 28 different ways to replace it with a different character. Same with the third character. Thus, we have 28 times 140 characters in our message, and each character has 28 different ways to be replaced. So thus we have 3,920 different ways. E is asking how many have exactly 6 spaces and 5 commas. Well, we could use combinatorics for this. So given that we have 140 characters in our message, we want to choose 6 of these spaces to be representing spaces. So you can think of this as 140 blank spaces, and we want to choose 6 of these blank spaces to represent our spaces. So we have 142 6, representing all the different possibilities. We could select 6 to be our spaces. And we're now, because we selected our spaces, we only have 134 characters left in our message to fill in. And we want to fill 5 to be our commas. So that means out of the 134 blanks left, we choose 5 to represent our commas. After that, we now have exactly 6 spaces and 5 commas. So now we can just fill in the rest of the blank spaces with any other character. Given that we already used spaces and commas, now we only have 27 different characters left to choose from. So thus we have a 27 to 129th power to represent the remaining spaces, and this concludes the answer to having how many messages have exactly 6 spaces and 5 commas. Symmetry is asking us how many length 7 bit strings have more zeros than ones. Well, if you think about this, a length of 7 bit string could either only have more zeros or more ones. So in this case, a total of each character only can be 0 or 1, so there's only 2 possibilities, and there's 7 of these blank spaces to fill in. Thus, we have 2 to the 7th power as our total number of possibilities to fill in a 7-length bit string. And given that there's only 2 ways, either being more zeros or more ones, thus we can just divide this by 2 to get 64 possibilities of having more zeros. Another way to think about this is you have 7 spaces to fill in, we wanted to find 4 to represent our zeros. And we know that 4 out of the 7 is more zeros, so we found all the possible ways to get 4 zeros. We want to add the possibilities of getting 5 zeros, 6 zeros, and 7 zeros. In this case, all of them being zeros is just a case of 1. So if you add all these combinatorics, you should get 64 as well. Part B is saying how many length 8 bit strings have more zeros than ones. Note that because we're now using an even number of even length bit string, that means we can also include the scenario of there being a tie because there could be 4 zeros and 4 ones. Note that we could use a similar case where we choose 5 to be our zeros, 6 to be our zeros, 7 to be our zeros, and 8 to be our zeros to find all the possibilities of having more zeros than ones, which you should get 93. Another way to think about this is there's 2 to the 8th power different possibilities to fill in our 8 length bit string, and we want to subtract all the possibilities of there being a tie, which is 8 choose 4. Or you could just say that there's 8 blank spaces and we want to fill in 4 of them to be our zeros, and then the rest fills in with 1. So now that we removed all the possibilities of being a tie, we divide this by 2 because now we only have the scenarios of being more ones or more zeros. And you should also find that this also equals to 93. For equations, how many solutions does x plus y plus z equals 10 have if all variables must be positive integers? Well, you could think of this in terms of stars and bars, where we have 3 bins, each bin representing x, y, and z, and we have 10 balls to throw in. So because we want all variables to be positive, we want to first fill in each bin with 1 ball to make them positive. Because if we don't, we also include the scenarios where a bin could be empty, which means there's 0, and 0 is not positive. So in terms of stars and bars, given that we have 3 bins, this can be denoted with 2 bars. See, in this case, for 10 balls, we could fill in 3 balls for the first bin, 3 balls for the second bin, and 4 balls for the third bin. And the bars split it up into 3 bins. So thus there will be always 1 less bar than the total number of bins. So thus we have 7 balls left, since we want to fill in each bin with 1 ball to make them positive, 2 to represent our bars, to separate our bins, and choose 2 to fill in. Given that we have a total of 9 blank spaces, we want to choose 2 to represent our bars. Thus we're left with 9 choose 2, or 36. Note that 9 choose 2 is also equal to 9 choose 7, where instead of choosing 2 spaces to be our bars, now we're selecting 7 spaces to represent our balls, and then the rest will be filled in with the bins, or the bars. B is asking how many solutions does x1 plus x2 plus x3 plus x4 equal 20 have if all variables must be non-negative and x1 and x2 has to be less than 8. So similar to the case with part A, we have 4 bins to denote the 4 variables and 20 to represent 20 balls. So in total, we have 20 balls plus 3 because remember there's always 1 less bar to denote the number of bins. So now instead of 4, we use 3 to represent our bars, and we choose 3 of those spaces to represent the bars. Note that this also equals to 23 choose 20, where in this case, instead of choosing the bars first, we choose 20 blank spaces to represent our balls. So 23 choose 20 is equal to 1,771. So in total, there's 1,771 total possibilities to be our 4 variables. So now we have to include the case where x1 is less than 8. So we can think of the cases where x1 is greater than 7. So we find all the ways that we have x1 being greater than 7, so we can just subtract that number of possibilities from our total. So now we can think of x1, in this case, this bin, is already filled up with 8 balls, just to note that is or greater than 7. Because our question is asking x1 to be less than 8. Thus, we have 3 empty bins to denote x2, x3, and x4. So thus, now, because we already used 8 balls, we have 12 balls left to fill in our bins, and the 3 to represent our bars. So 12 plus 3, choose 3, is 455. Note that we could also do, say, a similar case or symmetrical case to x2 being less than 8. So in this case, we're trying to find all the possible cases where x2 is greater than 7. So if it's greater than 7, that means x2 has to be filled in with 8 balls, just to denote that x2 is greater than 7, and we find all those possible cases. So this is a similar case to x1 being greater than 7, so it's 12 plus 3, choose 3, or 455. So that's why we subtract 455 twice, just to denote x1 being greater than 7 and x2 being greater than 7. But because this double counts, since we also include the cases where both x1 and x2 are both greater than 7, we have to add back the case where x1 and x2 are greater than 7. So we can fill in x1 and x2 to be 8 balls, so thus we're left with only 4 balls left to throw into the 4 bins. So we have 4, and we have 3 to represent our bars, choose 3, thus we are left with 35. So that means we add 35 back since we double counted, so in total we have 895 total ways where all variables must be non-negative and x1 and x2 are both less than 8.